Okay, so last time we talked about angular impulse and angular momentum, and extending the ideas from our discussion of linear impulse and linear momentum from particles. We're able to now fully describe impacts of rigid bodies. This video is just going to be an introduction to the applying the method, applying the analytical technique for analyzing angular momentums and the true, well, all of the momentums involved in a collision. And we'll go over one example, and then the next video will have a more rigorous example, more detailed example. Okay, so we are dealing with two rigid bodies in 2D planar motion. So all of the motion is limited to a single plane. So they then exist in the same plane. So they're in planar motion in the same plane, okay, and then they collide. Okay, let's have a little bit of a picture. We'll talk about just generally what can occur here, right? So if there's an object, we'll call this rigid body A, and then we have maybe rigid body B over here. Put them fairly close, as if they have a little bit of ways to go yet to collide, but the collision is imminent. Yeah, so let's say their velocities, right? So maybe A is moving, A's center of mass is moving this way, and then there's a rotation about that point currently for A. So this would be omega A with velocity of A there. And then let's say B has something similar, so it's moving that way, its center of mass, VB, and then it has, I don't know, it doesn't much matter, it's rotating there. So that is omega B. I'm just making these points up, right? Making these dynamical situation up. Okay, and then as they move, right, maybe because this moves here and this moves here, they make contact there with that point, let's say, right? And so then this would be the collision, the force that the two would have on each other. So this would really be some resultant force, and it has to be normal to the surface, right? It's really a normal force of impact. Okay, and it's equal and opposite to one another. Okay. In general, right, these types of systems, these impacts, these collisions, deal with translation. We're just making maybe some observations here, and that'll lead us to talking about the procedure when we go to analyze these in like the examples, or actually working through problems. In general, we have to think about translation and rotation because these are rigid bodies, right? In order to even describe the system, we have to talk about that, A is moving that way but rotating, right? Like that. And then B is moving this way but rotating that way, right? And so this motion, see if I can do it with two. This motion of this one moving, and rotating that way, and this one moving there but rotating this way. Well, it's hard for me, right? They kind of go like that and hit each other at some point. Is dealing both translation and rotation. Because we're talking about a collision and these are true bodies, mechanical energy, so our kinetic energy combined with potential energy, is not conserved in this process. So we can't go to work energy during the collision, right? As soon as the collision is over, you can go back to work energy. Right before the collision, you can go back to work energy, but in that instant of during the collision, as they're making contact, mechanical energy is not conserved. So typically, in general, it's also an inelastic collision. So kinetic energy is also not conserved. All right. But definitely mechanical energy is not conserved, right? There's some friction, there's some non-conservative forces here, right? There's friction, there's heat generated by the collision, there's a deformation of the material, there's noise being created in collisions. All of these are now losses in mechanical energy. internal forces, like these R's we have there, internal force pairs, right, equal and opposite in terms of the isolated system of the AB combined system here, right? Internal force pairs then contribute zero net impulse to the system. All right, so we'll be able to use that idea, right? So if you know, and as we've seen before, right, if R is equal and opposite, and we treat the whole thing as a system for our either linear momentum or even angular momentum. Angular momentum, we'd have to, you know, say, well, what's the moment here? But they basically contribute nothing if we decide to analyze the system as a pair, as a whole. Okay. Last observation, last statement to make about these. Often convenient to pick a fixed point to analyze the moments, right? Because there's going to be both a linear, right? Because we're dealing with translation and rotation, there's going to be a linear momentum analysis and an angular momentum analysis. Often convenient to pick a fixed point to do our moments. This is instead of the center of mass, which which often is a convenient choice. Here it's the center of mass because that doesn't require like tracking this as the collision occurs or like before and after. So if we were to choose the mass center to do this, then that must be tracked throughout the collision, before and after, basically, right? Okay. So we need to know where it's headed in the end. Whereas if we pick a fixed point like this would be a good choice, right? Like this point P where the collision occurs, right? Because over the collision, that point, you know, the bodies are sticking to each other, and that's not going to be a point that that's not going to be moving. Okay. So let's talk about the general procedure. We'll get into one example here, and like I said, the next video will have an even more detailed example. The next lecture. So our procedure here for impact analysis with momentum and impulse. Well, often we try to avoid any of the calculations of impulse and just have a conservation of momentum. We'll see if we can get there, right? Okay, so first we always start with the free body diagram to make sure we're having, you know, including all the forces in our analysis, so that we're not, you know, saying there's zero impulse when actually there is, because there was a reaction force that we forgot about, right? We then find a point or points where when we sum up moments about that point O, okay, remember this is point O, angular momentum is conserved. Okay, that's going to be the key to these rigid bodies. And then also we check, now we can't pick points here, but we can check if some of the forces, because this would be global to our, you know, rigid body or our system of rigid bodies, check if that's true, and if that's the case, then linear momentum is conserved, and we can also use that as a tool. Not always, right? So now if we've picked a good point and our angular momentum is conserved, then we can apply, right, first body plus the second body's angular momentum is constant, or maybe it's just a single body is constant and the other body separately is constant. This is now how what did you consider as your system here? Which one is going to give you the better, right? There's different choices, right? So it's either this or that. Yeah. Okay. Oh, we're not to 4 yet, because then if linear momentum is conserved, question mark, right? We had to check it in step 2. So if you confirm that it is, then we can apply the linear momentum of the two objects is constant. Now this one usually comes in a pair. We don't usually just analyze just a single particle here, or a single body here. Right? And these are their center of masses, right? Velocity at A, velocity at B. Center of mass velocities. Okay. Step 4, or kind of part 4 of these problems, again, often, I think when you're first starting out doing these types of, mechanics problems, any kind of mechanics problems, good to follow a procedure. And then when you get comfortable with it, along the way, be like, oh, you know what, I'm going to need this velocity relationship. I can sneak this in when I'm working through an earlier step. So, if kinematics part of that shows up earlier, or geometry shows up first thing, with a free body diagram, great, but just know that these are all components of a problem. Kinematics as required, and geometry, I say. Okay, I already talked, maybe you're having to calculate a moment of inertia. Do you do that at the start? Do you do that down here, right? And then this should then allow you to solve. And note, maybe at this point you would also be combining this with after the collision. Maybe the information you have is well before the collision and well after the collision. All right, so if you have information that, a velocity, something started up at a height, gained kinetic energy by dropping, well, that's work energy analysis, and then made a collision with two bodies, and then did something afterward and went to some new position, and that you have information about the position, you'd have to do work energy, conservation of momentum for the collision, and then back to work energy. So it can be combined with work energy analysis. Okay. All right, so let's get into an example of this procedure. What we have is a slender bar. Doesn't look like it too much in my diagram, but we'll treat it as a slender bar. OA, given mass here, initially sitting there at rest and then struck by a bullet, which was traveling quite fast at 400 meters per second with a tiny little mass, right? So, moderate momentum, right? Because the momentum is the mass times the velocity. But at this angle, kind of heading downward at an angle here 30 degrees from the horizontal. Afterwards, B then impacts inside of OA. We want to determine the angular velocity immediately after impact. Okay, so, right. So this, let's put that in here, right? So we expect it to be, well, if it's coming out at us, right, and we expect the resulting omega to be that, okay? And we label it the angular velocity of omega OA, of the bar OA. Okay, let's put in a coordinate system, right? So we'll use O up here as our coordinate, or as our origin of the coordinate system. There's X and Y, and so associated with that, right? I always like to put this in my diagrams. This is going to be the I hat direction, J hat, and then K hat is coming out at us. Okay. All right, let's get into it. So first step here is our free body diagram, as always. We'll put it up top. Yeah, I think we can put it up here. Okay. Free body diagram. And this is going to be for the system of bar and bullet at impact, or during the impact. Okay. So I'll put in there what the force is on each other, but for the whole system is what we're trying to get to here. Okay, so we got a pin up here at O. We've got A down here at the end of the bar. We've got reactions because of this pin, right? This is going to be the X force at O and the Y force at O. Those aren't zeros, those are O's. Right in the center of mass of the bar, we have its mass, and we also, or its weight. And then down here, where the bullet is, represented by maybe a dot together with its center of mass, which is it's just a particle, right? So here we have the mass of the bullet, so we'll call that B times G, and then this here is the, it should probably be a bigger one, that one's much heavier, mass of OA times G. And that's it, okay? Now, we also have, if we were drawing independent systems here, we would have the force, which could be quite complicated. This is going to be the force on the bar, OA, right, from the bullet, and then equal and opposite to it is the force, and this is at any time shot during the collision here. This is the force of the bar on the bullet. All right, and those are equal and opposite. So if we take the whole system, those cancel. This is what we mean by internal forces to a system cancel out. And again, what we want to do is analyze the momentum before the collision, after the collision, and if there was any, if we're just analyzing the bar, let's say, right, this is going to be changing in time because this is due to the bullet and during the collision, and we would need to integrate that as an impulse, right? And we'd like to avoid that, and so we're going to take the whole system as what we're analyzing. Okay, so into step 2 here, which is our equations of motion, EOMs. Okay, some of the moments are then 0. Or actually here, I'm sorry, this is, well, equations of motion. Well, what we're actually doing is, do we have conservation? So let's just, and that's what I just justified, right? Yes, we do. So let's say that. Angular momentum conserved about O. If we didn't do it about O, then we need to consider these reaction forces. But their line of action is right through the point. In fact, all of their lines of action about O. So we got no moments. No moments about O. Okay? Smart choice because of the horizontal reaction force there. Now, note, when we look at linear momentum, that's not conserved. Not conserved due to the reaction forces at O. Okay, so what we mean is during this collision, the sum of the forces external is not equal to 0. And that's because these might change in time as the thing starts accelerating and changing its motion. So all we have to work with is basically angular momentum conservation. Okay, let's now move on to step 3, which is actually applying our conservation rule. So since linear momentum is conserved, we're going to take, for the whole system, right, and we're going to take the linear momentum about point O for our A object, right, so for the bar, at state 1, add it to that angular momentum about O for the bullet at state 1. This is before collision. And then that equals the same things for after. So OA2 plus HOB2. Okay? Take each of these one by one. Well, this is 0 because originally the bar is at rest in state 1. Should we categorize these, right? So this is just before collision, before impact, and this is after being embedded. After impact. All right, so that's what we mean by a two-state analysis here. Okay, so this one's at rest. Let's see, what's the linear or the angular momentum for the bullet? Well, the bullet is a particle, right? We treat it just like a particle because it's such a all that mass is accumulated into one like little space at a point. So we call that a particle, and we go back to our particle relationships, right? And so, that took on the form R. So the position vector of B from the origin, from our origin of our coordinate system, where we're doing, taking the moments about, crossed into its linear momentum, M, V, B in the first state. Okay. Now this equals. Okay, so now here, this is, okay, here we're going to have particle again. Okay, so let's write this one. So this is going to be the same type of a term we had over there, which is RB naught crossed into MB VB2. Okay? The one in the middle, though, this is a, we've got fixed point rotation, right? So we're going to be using the form of the angular momentum about a fixed point, not its center of mass, right, which would be somewhere like there. Okay? Not G. So this term I'm going to put here is for a fixed point. Okay? So that is the moment of inertia about that fixed point times the rotation of the rigid body, k hat. And this makes up our equation, right? Okay, now we do some kinematics here. Take a side step here to do some analysis on the side. Let's see, what do we have to do? Well, looking at this equation, we need to determine this position vector that shows up twice. Determine this, and what we mean by this is, well, we know its magnitude is 400 meters per second, but what are its components? We're going to need the components to then break it up into, to do this cross product. We'll need the moment of inertia for the slender bar, and we'll need to relate this. If we want to solve for omega A, we need to then relate this to omega A, because that's there, that's fine. I think everything else is either specified directly. All right, so we basically have 4 things to determine, okay? Okay, so the first thing, that position vector of B with respect to the origin of the coordinate system, that's just minus 0.75 j hat. All right, and the units on that would be meters. And all we're doing is starting up at O, going down 0.75 to get to that B location. Okay, so that one's not too bad. Let's see. Next thing we need is VB1. Can we get that? Well, we can, right? We know that it's 400 meters per second in magnitude. 400. But what are its components? Well, do we need to draw a little triangle here? I think so. Maybe we can fit it in there. Okay, so that's VB1 in its full magnitude. Its components in the horizontal and the vertical are going to make up this triangle with 30 degrees. Okay, so the horizontal is the cosine component, right? So we have cosine of 30 degrees, I hat plus sine of 30 degrees, j hat. And the units here are meter per second. But cosine 30 degrees is root 2 over 2. I'm sorry, root 3 over 2. Square root 3 over 2. And then sine of 30 degrees is a half. So we can write this as 200 root 3 I hat plus, oh, and that's negative. We went down in the j hat direction. So minus 200, because we have a sine of 30 degrees is a half j hat. Okay, and the units there are meter per second. Okay, next kinematics, relationship or geometry. Oh, I almost knocked the board over there. Okay, I naught, we need to get, right, if we're chucking through our equation, we got that, we know the mass, we now have that in terms of its components. We need the moment of inertia about point O. So that's a slender rod about its end, so that's going to be the mass of OA. Oh, and by the way, we should be careful here, this is mass B. I got it over there, didn't put it here. This is the mass of the bullet, that tiny little mass. Anything else missing? No, I think we're good. I mean, maybe it'll come up. Okay, so this is going to be the mass of, so the relationship for a slender rod about its end is ml squared over 3. So this is a ml squared over 3, which we know all of these, right? So this is 5 kilograms. The length is just 1 meter, 0.75 plus 0.25. So squaring that is really trivial. Divided by 3, we get 1.66 forever. We'll chop it off after a little while. And the units here are kilogram meter squared. Okay, and the last one now is, can we get a relationship between the last thing that's unknown, right? So this is what we're solving for. That's okay. That we've determined, and now this is the last thing we need to know. Well, we're not going to be able to know it. In fact, all we're going to do is relate it to the unknown, omega A, and then we have enough, right? So VB at 2, now that has, it's the velocity of this point right there, right? Well, as this thing swings upward, right, it's going to have a velocity like right, it's just like a point on the rigid body during this motion of rotational motion because the whole bar is pinned. So this is VB2. And let's see. Well, we can relate it to point O because they are now attached to the same rigid body. V naught O plus omega OA crossed into that relative position vector to get to B from O. Okay? Well, O is pinned, so that is 0. And this then is just the, let's start calling this, yeah, we can just call it omega OA. Let's give it something else, right? Let's, just so we can clean up our notation. We'll call this the rotation in state 2, right? It's the rotation of the whole system as the whole system rotates after the impact, okay? That one didn't come off with just simply. So we will call this omega 2. Okay, so this is just omega 2 k hat crossed into that position vector that we have up there, which is minus 0.75 j hat. K cross j is in the negative I hat direction. With that negative sign makes it a positive. So 0.75 omega 2, that's what we're solving for, I hat. Okay. That's good, right? So now we can plug all of these things into our momentum, angular momentum conservation. And we have enough to solve for, right? So that's 5 here. Step 5 is to solve. Okay, let's see if we can fit it in. Okay, negative point, now we have everything. We're just going to be plugging them in. That's minus 0.75 in the j hat direction. Crossed into mass, that's the mass of the bullet, so it's 0.004 kilograms. And then we have the 200 times root 3 I hat minus 200 j hat term. Okay, that's the whole left-hand side. Equals, this term is the moment of inertia is 1.6667, as many sixes as you like. Omega 2, now we're calling that omega 2. And that's in the k hat direction. In fact, because it's planar motion, these should all be in the k hat direction eventually. Should be the only non-zero terms. Plus this last term, which again we have minus 0.75 j hat for that relative position vector, crossed into 0.004 multiplied by VB2, which we've now written in terms of omega 2 as 0.75, 0.75 omega 2 in the I hat. Okay. Let's see now. Let's take this term by term, and maybe we'll do a unit check afterwards. But first, we got a j hat crossed into an I hat. J crossed into I is going to be minus k hat, canceling that negative sign there. Okay. So, and then the term, the actual calculation, 0.75 times 0.004 times 200 root 3 gives you 1.0392 k hat. Okay, and again, I'll mention the units here in a second. Now this term is an omega 2, so both of these terms are going to have omega 2 in them. You see that? Oh, I forgot to mention. And then j hat crossed into j hat is 0. Right? You wonder what happened to this term over here. Well, that's j hat crossed into I hat. When you do these multiplicated out, you get the 1.0392. And then you have the j hat crossed into j hat. That is 0. Any cross product in the same direction, two vectors in the same direction, is 0. Okay, on the right-hand side, both terms are going to have omega 2. Any term in here is going to have an omega 2. And we only have two terms, right? So it's going to be 1.6667. Is it plus or minus something? Well, we have j hat crossed into I hat. We already talked about that. J hat crossed into I hat is negative k hat. With the negative there, those cancel. And when you do this multiplication out, you get 0 because the 0.004 is so small. This is 0.00225. And in fact, we could probably just neglect this term, right? What that is the momentum, or the angular momentum of the bullet. And that's just this like little added mass we put right there. Oftentimes we just neglect that term. You can see why. It's so much smaller. Both of these are then in the k hat direction. And all we'd have to do then is take, add those together, divide it to the other side, and we get omega 2 equals 0.6227 radian per second. Okay. And that would be it, but I do want to just do a quick check of our units, because I said I would. So maybe I'll put in here what the units are, right? So this is a meter. This is a kilogram. Okay. These both were meters per second. These came from our velocity. Okay, so these are meter per second. So this term on top should be kilogram meter squared per second. Is that right? Yep, kilogram meter per second. So on the left-hand side, we had kilogram meter squared per second. And on the right-hand side, what was the 1.667? That was a moment of inertia, which is kilogram meter squared. Kilogram meter squared for the moment of inertia. And then we have an omega 2. That's what we're solving for. So that would be the thing so it would be kilogram meter squared times the units of omega. Just checking our work here. We can also check the second term, right? What's out front here is a meter. Okay, this is a kilogram. All right, so the units here are the same as the other one, except this 0.75 is also just another meter. Okay, and so again, we have kilogram meter squared. All right, so both terms on the right are kilogram meter squared times an omega, which is what we're looking for. So if we compare this, right, the only way this works is if omega's units are 1/second, which is what we want, radians per second, okay? Quick check of the units helps us catch blatant mistakes. When the equations don't have the right units, we know there's an algebra mistake somewhere. So it's always good to go back and check that, especially if you have time in an exam setting. It's a great place to do that. Okay, so reviewing this one, right, we added a small little mass, but it came in with some momentum. It actually provided angular momentum about a pinned point in the system.